Hello, I'm Rita Pucci from the University of Udine, and today I'm going to present to you our work on self-attention agreement among capsules for image classification task. We firstly introduce the concept of entity. An entity is an object or an object part that can be seen in an image. Entities are used for the classification of computer objects or scenes. For example, we can say that because I can recognize a circle, 2 eyes, 1 nose, and 1 mouth, I can recognize a face. How to identify entities in the image? Among the techniques at the state of the art, we focus on capsules. A capsule is a group of neurons trained to depict properties of entities identified in the image, like position, size, texture. The baseline architecture of capsule is CapsNet, introduced by Sabor. The architecture consists of an initial convolutional module to extract features, followed by capsules layer. The output of each capsule is composed by activity vectors. Each activity vector consists of the activations values of the capsule's neurons, and it represents the point of view of the capsule and the properties identified for the entities in the image. The different point of view obtained by capsules are aggregated through routing by agreement in order to identify the object that brings together the properties extracted by the capsules. This process is innovative, but iterative, and causes an increased computational cost. Moreover, it is hard to train with backpropagation and hard to be interpreted. Let's move the attention to a similar idea, the attention layers in transformers. Transformers consist of deep neural networks where the self-attention layers are stacked on top of each other. Each layer computes a representation of the input based on the properties identified in the previous layer. In this model, we focus on the multi-head attention module that runs the attention layer mechanism several times in parallel. It improves the attention at the higher layer for the vectors with a larger attention at the lower layer. The idea behind these two mechanisms is similar. Both want to extract the probability distribution to describe how lower layers that can identify entity pairs are connected with higher layers that identify entity objects. Let's have a deeper look to the two mechanisms. The input in both is the output for the lower layer. In case of routing, it is used straight in the mechanism. In case of attention, it is transformed in query, key, and value matrices. So the first step is computing votes. Both compute votes over the input. For routing, the votes are obtained by affine transformation by the matrix weights W. And in attention, votes are obtained by dot products among the query and key matrices, then normalized. The probability of an object of being present is computed by an iterative procedure that computes how much each capsule at lower layer is effectively important for the higher layer by the coefficient C, and then aggregate the probability of based on the agreement among capsules. In case of attention layer, this probability is computed in a straightforward path, where similarity among the lower layer outputs is computed by the attention with the function softmax. In this work, we propose the use of outputs of capsules as inputs of the self-attention layer. To do so, we take CapsNet architecture. We move the two last layers of classification, and we pass the output of capsules to the attention mechanism. Each head at the multi-head module receives the output of a single capsule in order to obtain heads specialized to compute attention for a dedicated capsule. The independent attention outputs are then remapped over the expected dimension, the number of classes. At the end, we obtain a feature map based on attention for each class. So let's put together. We propose the Attention Agreement Caps architecture. The capsules perform the extraction of properties of entities identified in the image that are transformed and aggregated by self-attention layer. The feature map obtained are summed to obtain for each class a vector, and the class is based on the norm of the vector. We evaluated the AA caps over 5 benchmark datasets, and the proposed new baseline outperformed the CapsNet baseline for Cipher10, small norm, and any more with attribute datasets. But for NIST and street view numbers, we obtain really competitive results for accuracy. To conclude, by replacing the routing by agreement with self-attention layer, we remove the iterative mechanism, obtaining a lower computational cost, and also the model has competitive performance with less trainable parameters. Thank you for your attention.